Welcome to today's webinar. Today we'll show you how you can calculate a laminated glass panel in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, newsletters, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. The presentation will be done by my colleague Ulrich Lex. He is responsible for the product development of RFEM 6 and the main responsible person for the add-ons glass design, masonry design, and construction stages analysis. And he works in the customer support team as well. Okay, then I say something how you can ask questions. At first I switch off my webcam that you can see the full screen. Now, if you have a question, just press the button with the question mark, then enter your question in that field, press send, and I will receive your question, and then I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Ulrich. Ulrich, you can start.
Thank you very much, Andreas, for your introduction. From my side, also hello to today's webinar. Today, I have prepared a topic for modeling and calculation of a laminated glass surface. In the second part of the webinar, I want to show how is it possible to create an insulating glass unit manually in RFEM, and as a last part, the design and documentation of the glass structures. Therefore, I want to switch to the program and share the screen. So I have prepared a new file. When you start with a new file, then you get the dialog of the base data. Here you can enter your model name and so on. The more important thing are the add-ons and the standards. For the add-ons, you can check on the needed design add-on. For example, today our glass design add-on. There are a lot of different add-ons for other materials to design, maybe steel, concrete, or only a stress strain analysis. And we have also a lot of add-ons for analysis, nonlinear behavior, structure stability, construction stages, and so on. And also we have add-ons for the dynamic analysis. You can each add-on check on or off as you need it. The second part are the standards. Here you can choose which standard you want to compute and design your structure. For the load case and classification, we want today use the DIN 18008 for the glass design. So I choose for the load classification this standard, and also for glass design. For glass design, we have implemented the ASTM E1300 and a design, only a stress design without standard. We are working on a lot of different additional standards, like the upcoming hero code. So if you have done the settings, so you can continue with OK. When we start with the modeling, I work for my glass structures in a working plane XZ, and I have changed my grid to 0.1 meters for today's example. So I want to start to create a new surface. There are a lot of different possibilities in RFEM. Today I want to use to create a new line, maybe with a distance from 1.1 meters and a height of 1.4 meters. So to complete the structure, I copy my two lines to the right place. So as a next step, I want to add a surface to these lines. I want to choose the select boundary lines. You could also create a rectangle surface without creating extra lines. It's up to you what you use here. So I want to create a new surface. A new surface needs to have a thickness. So today I want to create a new thickness that I can show you the important things. When I create a new thickness, I have thickness types, different thickness types. It's a uniform thickness type is the default setting. But when you choose the glass design add-on, then you get here a thickness type glass composition. When you choose this, you get a new tab with layers, and here you can directly create your glass composition. So here I have to start with the new material. Here the last materials are loaded. The last materials what you use maybe in a different file are loaded. You can also create a new material. Go to the material database, choose maybe only float glass, and you created a new material. Here you have to insert the thickness of your glass composition, and you can continue with the next layer. Here we can create additionally a new material, not for the glass, maybe for the foil. We want to use PVB. Okay. Set the thickness. And as the second glass part, create my composition. So the self-weight of the composition is computed automatically. You also can save different compositions as a template and read it in afterwards when you work more times with the same composition. So when you click OK, then the thickness is assigned automatically. Now we can choose our boundary lines, click with OK, and the new surface is created. So what's the next? The next would be to take a look at the supports. Here I have line supports and nodal supports. For the loads in Y direction, I want to use a line support, and for the self-weight maybe or the vertical loading, I want to use nodal supports who are from a distance from the edge are located. So I want to divide this line by a distance, maybe 0.2 meters. Okay, and the second from the other side, distance 0.2. Okay, and here I want to assign nodal supports. Create a new one. It's only supported in Z direction. Okay. The second one should be supported in Z direction and in the global X direction. Okay. And my line supports, create here a new one too, should be support the structure in global Y direction. Here I do not want to use a fixed support, even I want to use a high spring constant. To get a little bit smoother result on these lines. Okay, just go one step back. Here would be also the possibility to create a non-linearity. Maybe when I want to say, okay, my support should react as failure if the support reaction is negative. The setting could I do here in the support. Okay, and assign it to these lines. So this would be enough for the time. Here I created my surface with my thickness, with my glass composition, and the structure would be ready for calculation. Before I go to the next step for loading and so on, I want to create a second structure for a curved surface. This is also possible to compute with RFEM. There, I want to create a new curved surface. So I want to create my two nodes, and it should have a radius of 40 centimeters. Now I can create an arc. And this should be my geometry for the curved surface. I want to copy it in direction of Z. 1.4 meters. Okay, and complete it with the lines. So to assign a new surface, I had to use now not the plane surface. I had to use a quadrangle surface. It's here located here. Create a new surface as quadrangle. I can assign also the glass composition I created. Can continue with boundary lines. Click OK, and my surface my curved surface is created. So as the second part, I want to continue also with supports. Here I want to use the same system in horizontal direction. I want to use line supports, and for the vertical loading I want to use my nodal supports. For the curved structure I need here not only 2 points, I need 3 points to get not an instability at the surface. So I want to do the same. Select the line, click right, divide line by distance. I want to choose again the 0.2 meters. Now I want not divide the line. Then I have the option to create nodes online without dividing. I can click this here, continue with, just move the click apply, and for the second I can use the line end 0.2, click apply, and the second node is created. So for the third node, I can use 0.5. It should be directly in the middle. Continue with OK. And all three nodes are created. But it's not in the middle, so I can change it from start and end node. Okay, now it's better. Here I can assign again my nodal supports. Therefore, I want to create a new one. It should be fixed in X direction and Z direction. X and Z. Here I could use also number 7. But I want to create a new one. For the both side on the side, I want to use a different a special thing. So I want to use a specific direction. It only should be supported in Z direction. If you have it only supported in Z direction, you would not need it to change the direction. But I want to show it how it would be possible. So I use the option specific direction, could here use directed to a node, could say, okay, my x-axis is oriented to the midpoint of the curve, and it should be in the plane of x, y, and can continue with OK. OK, and choose this node. That means that this support is the axis system. That the axis system of the support is oriented to this midpoint of the surface. This would have the benefit that I can really exactly create the supports to this curved surface. As I said, if we have only fixed it in Z direction, it doesn't matter, but it would be important if it's fixed in the Y direction too. So the same I can create for the right support. I can create a new one. It's only in Z direction, specific direction. Okay. And the axis and the plane is here on. Okay. Okay, and assign this node. So perfectly. As next one, I want to assign the line supports. And for the line supports, it's the same. I have to look at first at my line orientation. So when I when I display the axis system of the lines, I see that the y direction of the arc is already oriented to the node. This you can also, the setting you can do also if you edit the line. Use here rotation, and the rotation is inside to the line. So for the side lines, I can do also the same. I can use here the rotation. I can use rotation to an help node, and can select here the center of the line. That means that also my y direction of this line is oriented to the center of the arch. The same I want to do here. Rotation help node here, and continue with OK. So now I can easily assign my line support. Click here, my local axis system. It's in y direction, and I use again my spring constant. OK. And assign here all the lines. So if I take a look in that direction on the system, then I see it's pretty nice. All my supports are oriented to the center of the arch. That means I get no forces into the system what I do not want to have. So as a next step, we can continue with the loading. For the loading, this load case for self-void is created automatically. Here I can go to the dialog load cases and combinations. At the beginning, we set here in the base data dialog the standard for DIN 18008 and choose the load combination with that. If this is chosen, then I get the tabs load cases, design situations, and load combinations. The load combinations are created automatically according to the load cases. You could also check off this wizard and create your own load combinations. But today I want to use it, so I let it as it is and create a new load case for the wind load. The benefit, if you choose here the standard of the class design for classification of the loads, then you get here the load duration automatically according the standard. So it's for self-void in this case and for wind load. Okay, as I said, I get the design situations according to standard, and after that, my load combinations I want to have. So I could continue with OK. My load case is created, and here I can assign a wind load, maybe as a surface load. It's acting in Y direction. I want to choose 0.8 kilonewton per square meter and assign it to this surface. Okay, and the next one I want to choose here is a local axis system in Z direction. Okay. Here I have to take a look how the local axis system is oriented. So Z direction is, so I have to use here a positive value for on wind pressure. So this is everything I have to do. I would also have the possibility to assign here maybe line loads or free line loads for a handrail or so on. One additional thing, if you choose the thickness for glass composition, then automatically for types of glass design are created a model for glass composition. Here for this glass composition models are a lot of information. Here is maybe the settings that you can consider shear coupling or not. By default, it's not considered the shear coupling, so you could change it here. Here you can see the stiffness matrix, what is used for the surface according your glass composition. Here are the information about the line supports and the nodal supports and so on. But in our case, we have not to change anything here. There are automatically created different composition models for different glass systems. So as the next step before the calculation, I have to take a look at the FE mesh settings. So by default, it's a FE mesh of 0.5 meters. For the glass design, I would recommend to use a little bit finer mesh, maybe 0.1 or 0.05 meters. If I do this setting, I can click OK and apply and can take a look at the FE mesh if it's fine or not. But I think in our case it's okay. So when I have done all the settings, then I can continue with calculation. Oh, just one thing I have forgot. When I have before the design, I have to select, or I have to take a look at the surface. When a design add-on is checked on the base data, then I get in the dialog of the surface at the end here the design properties. Now we have a thickness or material of glass, so I get the design properties for glass design. I can check it on if I want to design this surface or check it off when I do not want to design it. If it's checked on, I have here design configurations where I can use the default configuration where I can do different settings according to the standard. So now I have not to change here anything, so I let it as it is. I get also the possibility to do settings for the deflection. Here I have double supported surfaces, so it's okay, but I have to modify the reference length, maybe manually or by a boundary line. I can choose here the boundary line. Okay, it's 1.4 by the maximum boundary line, so I have to choose it manually from a line maybe, and get here the reference length of 1.1 meters. Otherwise, my check for deflection would be wrong. Okay, the second surface, I want to check it too. Here's a deflection. The reference length is 1.15 meters. It's okay. So now I could start the calculation. When I create here, when I go here to calculate all or calculate glass design. On this step, I want to switch to a different on a different file, or I want to create a different one, because with these two surfaces, I want to show you how would it possible to use here not only laminated glass. I want to show you how would it possible to create here insulating glasses from it. So I want to save the structure in a different file to EQ. Okay. And could show you how you have to do in this way. For my insulating glass, it should be so that I have two sides with my glass composition as it is, and in between I want to have a gas solid with 1.6 centimeters for my insulating glass unit. How can I do it? I can select my surface. Could go with the right click to extrude this surface to a solid. Here I have the possibility to extrude it in any direction. So I want to choose here my space of the insulating unit. It's minus 0.0016. It's 1. And click apply. Yes, the mesh is deleted. And now I created here a solid with a space of 1.6 centimeters. The same I can do for the curved surface. Here I can select this surface, choose the extrude function. Here's the same. I go 0.016 and click apply. So now the solid is created. So how I have to continue? Because now this solid is created. This solid has now a material of a glass material. That in the first step is wrong, because I do not have a whole glass surface, and because of the situation the solid was created, the side surface of my solid are now without thickness. But I have to modify this a little bit. So I can choose my side surface. Again, this should be the standard stiffness type with my glass composition. Okay, the same I have to do for my curved surface. I want to choose my stiffness type default, my glass composition, and okay, I can here take a look at the reference length. it's different from a line. Okay. The same I can do here, so that I do not forget it. Okay. So the next step would be to modify my side surface. My side surface of the insulating glass unit should be something like the spacer of the unit. So I need it in RFEM to bring the loads to my glass compositions. So I have created here a solid. This solid should be a gas solid afterwards. A gas solid, so the gas solid gets a pressure. If the wind load is acting with the pressure of this gas solid, the second surface is loaded too. But with my side surfaces, with my spacer, I would call it, should we be sure that the loads are not acting here on the spacer. So this spacer needs a little bit stiffness, that the wind load is acting on both surfaces. So I have to modify also the stiffness of this side surfaces. Here I want to use a standard surface. I can create here maybe a new material. I choose now, it doesn't matter how it is called. I want to use a new material. Maybe I can create here a new one. Call it spacer. This should get a small modulus of elasticity, and here a small shear modulus for this spacer. Okay, and the thickness of the spacer should be maybe 10 millimeters. Then this setting would be okay, I think. And continue with OK. So this I have to assign to all my side surfaces. In the system. Standard spacer, okay. And also here. Select change it spacer and continue with OK. So the next step would be the solid. The solid we have to modify too. So I have to select the solid. It should not be a standard solid. It should be now a gas solid. So I have to create a new material. Go to the data library, have here the option to choose a gas. Here I can choose different materials for gas, maybe argon or dry air. It's up to you. Then we have to create a new gas, maybe. Maybe here the standard the standard settings, I would say, and continue with OK. The same for the second one, gas, dry air, and here. Okay, so that's all we have to modify. Then we have to continue with the supports. Now I have my glass composition created, where I have a laminated glass, a gas, and a laminated glass. So the connection between both surfaces is only with this weak spacer material. So if I support now only one side, I would get an instability because the second composition is not supported. So I have maybe at least support also the surface in Z direction. And copy here my nodal supports. The same I want to do for the line. For the lines, select all and continue here. Okay, so the same I have to do here with my curved surface. Support. Okay. So, and also for the nodal supports. So, okay. Then we can continue. When we take a look in Z direction, we see the system is symmetrical, everything is perfect. So then we can continue with the loading. For the loading, for insulating glass, I have to create maybe additional load cases. My self weight is okay. My wind load is acting on the one side. It's okay too, but I have additional load cases maybe for changing the altitude, for the temperature difference, and for the atmospheric pressure difference. It's called for climatic loads summer and or winter. Today I want to create only the summer load case. Here I choose maybe a permanent load for the altitude difference, and I can create a new load case for actions due to climatic, for temperature and atmosphere pressure. So the temperature difference and the atmospheric pressure can be acting in the same action category, and the altitude difference is acting as a permanent load. If I have created it, I can continue and I can assign the loads. The altitude is given in the summer load case by a difference of 600 meters. This value of 600 meters, I can recalculate it to a surface load Buzzer factor 0.012. It's given in the literature. You can find these formulas for it. So I choose a surface load. And surface load with 7.2 kilonewton per square meters, and this is acting now that I get that my solid is getting bigger, I would say. So I can select here the second surface, this one, and this one for the negative value, and for the positive value it's the first one here and the second one here. Okay. So now this load is acting on this surface, and you see it, surface number 1, and this load is acting on surface number 1. So then I can continue with the pressure difference with the atmosphere. It's given by a value of 2 kilonewton per square meters, and it's acting in the same direction like the altitude difference. So I get here load case 4. It's 2 kilonewton per square meters, and it's acting surface 1 and surface 10. And the negative value, it's acting here on surface number 2 and surface number 3. Okay. The last load is the temperature difference. It's given by a difference of 20 degrees. Here I can use easily the option to set a solid load, or to use a solid load like temperature 20 degrees, and assign it to both solids. Okay. I do not have to take a look of the correct load distribution. Now I have a symmetric system, so both sides would get the same loads. But when I do not have a symmetric composition at outside or inside the surface, it would be the same, because we have one system. We have considered directly the gas between the surfaces, and the gas is really acting in this whole surface. So when the wind load is acting on the surface outside, so I get more pressure in my gas solid, and also the surface inside is acting is acting also for the wind load case. So we do not have to take any manual load distribution. It's doing automatically in the calculation. So now we have created all loads. As a next step, we have to take a look on the FE mesh again. Here it's really helpful if we get a nice FE mesh. So I can create it one time, generate the mesh, and I have also to take a look at the solid mesh, or it is helpful to take a look also on the solid mesh. So, and it seems that here some, how should I say, irregularities. So I have to try to modify it, and it works in this case that I use here a layered mesh. For this layered mesh, I have to optimize the surface here at the bottom. For the surface, we have by default integrated objects on, and here my nodes from the supports are integrated. So here I have to check off this automatic detection, to delete my nodes, continue with OK and OK. Now I can edit my solid, can say, okay, I want to have a mesh refinement. I want to use a layered mesh. My side surfaces are suppose a glass surface, continue with OK. The same I can do with my planar surface to be sure to get a good quality of the mesh. And now I can continue to generate the mesh again. So now I see it's really regular, and it's even more better as before. So with these things, we are ready with creation of the systems. We added the loads, and we are ready now to compute it. Here I want to use compute all. Then also the glass design is done. For the glass design, this is the settings I can find here on the bottom. We have here the option glass design. Here I find the design situations, or I can modify the design situations, what I want to design. I find my objects to design. By default are all objects with glass are designed. You see my the surfaces with the spacer are automatically deactivated for design. So we have to here nothing manual. And here I find a lot of additional informations. So if I have checked it, then I can continue with the calculation, calculate all. So here I see the calculation of for the load cases, for the load combinations, and so on, and at the end the calculation of the glass add-on. So here you see the status of each combination. Now they are ready. Then afterwards the design is done, and then it is okay. So when the calculation is finished, then you see two different results. On the one hand, the results for the static analysis are deformations, internal surface stresses as it is for RFEM itself, and you find the results for the glass design. When I take a look at the static analyze results, then I see here the glass, the deformations. I can check off the FE mesh. Maybe you can only select surface and take a look here on the wind load case maybe. So the results are very symmetric, so the loading seems to be okay, or the system seems to be okay. So here you find also for the static analyze, you find also the results for the solids. In our case are the gas solids. We find the pressure as a pressure in the gas pressure. We find the initial pressure. We find the overpressure. You can also see the volumina of the solid or the temperature. Maybe when we switch to the temperature load case, we see here the 39 degrees, and in the other the 19 degrees we set at the beginning. Okay, then we can switch to the glass design results. Here we have an overview about all design checks, and we have here design ratios on surfaces. We see that we have an red flag. It's here on the side surface. Here we have to check about what's wrong. To check it, you can double click on the results, then you get all the formulas what are calculated according the standard. You can see the results, and you can see why it's not okay. Okay, you can also see results through the thickness when you select the diagram at the surface point. Here you see on which place of the composition it is. It is maybe overloaded, and could modify this afterwards. All these things you can also print to the printout report to document the results. The printout report itself can be created in the main navigator at the end with right-click print new printout report, or create new printout report. If you do this, you have the option to select a lot of tables, a lot of results, what you want to see. You have static analysis results for the surface. You get also glass design results. If you click Save and Show, the printout report will be created and opened. Just One moment, so it's exactly the printed report is created. And you got here all results you want to have. So as I said, you can also print these pictures you show graphically with the option print to the printout report and document the results graphically. So here you have by the result tables, you have the option to show the results by the design ratios. You can show the results by the material. You can show the results by the separated layers. So this was all I want to show you today, what I have prepared today. Therefore, I want to say thank you for listening. I hope it was good for you. It was a good information. And with these words, I want to give back to Andreas. Thank you for all. Bye-bye.
Thank you, Ulrich, for your presentation. I have an additional hint. You can book our online courses, for example, the RFEM 6 course for beginners, the Eurocode 2 course for the reinforced concrete design with RFEM 6, the Eurocode 3 course for the steel design, the Eurocode 5 course for the timber design, and the Eurocode 8 course for the earthquake design. For more information, just scan the QR codes in the middle or click at the links at the bottom. And you can download the slides from the same page where you can find the recording models. And in the next days, you will get an email with a link to that page. And you will get also your attendee certificate. Okay. That should be also all from my side. I thank you for your attention. Thanks, Ulrich Lex, for your presentation. I wish all a nice rest of the day. Bye-bye.